Some thoughtful Valentine's Day person left these, so I invited you to serve yourself. Should you like a Valentine's Day chocolate treat? I don't know if any of these are the dark chocolate variety. That's what I prefer. You may well know that from a nutrition standpoint, the dark chocolate is quite good for you. The lighter stuff, not so good. You can research that on Google if you have not yet thought about such. Let's get on with completion of chapter 18. Given that we are now armed with the tools to take any water solution apart analytically to the degree where we can calculate correctly the concentration of any species in the system, regardless of the tininess of its molarity. If it is a species whose existence depends on pH. And most species in water solution have such existences. That makes this a very important tool. If you're going to do biochemistry, if you're going to do chemistry on any living thing on our planet, like people. Now, the issue at present
when somebody ordered a Valentine's
What is that?
gram. Remember with Dance Marathon, when someone ordered a Valentine's gram to a student in your class? It'll take 30 seconds. Can we sing to her?
Who are we talking about?
Tabor?
I don't know. There's a person in here?
Named Tabor? Can we just sing to her really fast?
Go ahead.
Okay.
Have your fun.
Thank you.
Hey, Tabor, can you come up to the front, please?
You have singing gram from an anonymous secret admirer.
Alright, 5, 6, 7, 8.
L is for the way you look at me. O is for the only one I see. D is very, very extraordinary. E is even more than anyone that you adore and love. Is all that I can give to you. Love is more than just a name for two. Two and love can make it. Take my heart and please don't break it. Love was made for me and you. Ow!
Thank you very much.
Far be it for me to interfere with such delightful activities. Now then, one issue which we have yet to wrestle with is, after writing a charge balance equation for any system, which we already know how to do, can we or can we not set the charge balance equation equal to a charge sum? Because if we're going to do arithmetic with the charge balance equation, it's likely the case that we need the charge sum value. Most of the time, a charge sum value for the system in question can be written directly from the label on the bottle. The M sub I value, like the iron nitrate solution. Why so? Because the only negative ion of consequence in the iron nitrate solution is nitrate ion. For the 0.010 molar iron nitrate solution, which we have so far considered, the nitrate ion molarity is 0.030, and that's the charge sum value. Why is that true? Because although nitrate ion is a principal species in that system, it's the only negative ion in the system of consequence. But does nitrate ion in the system engage in any chemistry which converts nitrate ion to anything else? No, why not? Why not? Because nitrate ion is a Bronsted base weaker than water. Upshot. Does the existence of nitrate ion in water solution depend, yes or no, on pH? No. So, there's a case where the charge sum follows directly from the label on the bottle. Now, how about 0.10 molar ammonium cyanide solution? Charge balance equation is simple. The only positive ions in the pot are ammonium ion and hydronium ion, negative ion, cyanide ion, hydroxide ion. I write the formula for cyanide ion like this because the negative charge is borne by the carbon atom. So if I write NCN, which is the way textbooks usually write it, then I'm going to have to write the negative charge, unless I put it like this. If I write it like this, people go, what the hell's that? So if I write it like this, like textbooks write it, you're going to think the negative charge is borne by the nitrogen atom, which is not correct. So contrary to the regular practice of writing formulas by writing the symbol of the atoms of lower electronegativity first, to keep with the structure and charge of cyanide ion, I'll prefer to write the formula like this. Now then, back to charge sum for this system. Well, the main acid-base reaction in this system is this. What does this reaction do? It converts ions to molecules, species which don't bear charge. So if this reaction goes to an appreciable extent, we're hard-pressed to set the charge balance equation equal to a charge sum. Because from the recipe on the bottle, the label on the bottle, you might argue that the charge sum is 0.10. But if this reaction goes to an appreciable extent, which it does, and we'll demonstrate that in a moment, is the charge sum for this system greater or smaller than 0.10? Smaller it has to be, because we're converting principal ion species to principal molecular species if this reaction goes to an appreciable extent. So this brings us about to another realization. If you're going to write the PSI for this system, you think ammonium ion and cyanide ion in addition to solvent water is the correct PSI? Is that the correct PSI for this system? There's the label on the bottle. Is ammonium ion, cyanide ion, and water the correct PSI for this system? Yes or no?
No.
No, why not? Well, the answer to the question depends on whether or not this goes to an appreciable extent. Because if it does, in addition to ammonium ion and cyanide ion, we have to add HCN and ammonia formulas. Or if it goes to, practically speaking, 100%, then we won't even have ammonium ion and cyanide ion in the system. But we can start by realizing that ammonium ion and cyanide ion are certainly principal species in this system. Why is that true? Do we know that this reaction goes to an extent which is on the order of 50%? Look at the acid-base table. Because our gee whiz rule of thumb is to decide on reaction extent, compare product acid strength to reactant acid strength, or product base to reactant base. Doesn't make any difference, you get the same answer. What's the measure of strength for the product acid HCN? Its Ka value, 6.2 times 10 to minus 10. And the measure of strength for ammonium ion, its Ka value, 5.6 times 10 to minus 10. So what do we realize? The product acid is stronger, but is it much stronger? No. So without even doing any arithmetic, you can make a fair gee whiz estimation of the extent of this reaction. What is your estimate? Close to 50%? Because the acids are very close to each other in strength? But a little bit less than 50%. because the product acid is somewhat stronger than the reactant acid. Hey, we're just putting to use the stuff we've already considered, but now in greater detail. Now then, if we wanted to get the charged sum, then we've got to get a numerical handle on the extent of this reaction. And in order to get the numerical handle on the extent of this reaction, or more to the point, calculate ionization extent of this reaction, we've got to get its K value. Now, you were talking about how to get K values, at least some of you, in this week's discussion class. I don't know that all the discussion classes got quite this far, but let's make a comment. Did you or did you not, in 2045, learn the foundation considerations which will allow you to calculate K for any reaction, no matter how complex the reaction is? Yes, you did. What was that fundamental consideration? Hess's law. Hess's law. That's it. Now in 2045, you didn't use Hess's law to calculate Ks. But you did use Hess's law to do what? You recognize with the application of Hess's law that if you take two or more reaction equations and add them together, as if they were algebra statements, to generate a new, different resultant reaction equation. Since thermodynamic properties of chemical systems are state functions, Hess's law told you that if you have the heat of reaction for the different reactions whose sums you took, then the final reaction, the resultant reaction, has a heat of reaction that's equal to the sum of the heat of reactions which you summed up. Remember that? That's all you need. Because what we're doing in getting a K by the same process for a new different reaction is to add the changes in standard free energies for the reaction. Now, I doubt that you talked about changes in standard free energy for reactions in 2045 lecture. Did you? Anybody? Were you asked in your last semester's experience, were you asked at all to pay attention to changes in standard free energies for reactions? Were you in 2045 lab last semester? Then you sure as hell were asked to pay attention to this consideration. Because I knew this was coming, and that's why I put this stuff in the discussion for the solutions experiment assignment 7. Does that jog your memory somewhat? Unfortunately, the administration of this university has forced bastardization of 2045 lab by creating teams, the only purpose of which is to allow UF to enroll more students in 2045 than should be allowed. Because in laboratory, work should be strictly on an individual basis. Then most of you folks would pay attention to this stuff. You'd have no choice. But it isn't your fault. But I will say at this stage of the game, for a look at some of the fundamentals which relate to this, that we're going to look at detail, we're going to look at in detail when we get to chapters 20 and 21, not too far down the road. Look at the discussion for assignment 7 in your 2045L lab book, hoping that you haven't burned it, or thrown it away, or given it away, or sold it, or junked it. In some. And you'll see this relationship on our information sheet, which you have a copy of. I refer to this. Change in standard free energy for a reaction. G symbolizes free energy. ideal gas constant, temperature in Kelvin, log of the equilibrium constant. So, by appreciating this formula, which is derived from fundamental thermodynamic considerations, more on that in the future, we have a handle on K for a reaction through its delta G0 value. And Hess's law tells us if we put together two or more reactions to get a new different resultant reaction and have available the delta G0s for these reactions, then we also have available the Ks for these reactions. So if we add up the delta G0s for the reactions combined, we can get delta G0 for the resultant reaction, which means for the resultant reaction we can get its K. But rather than go through this arithmetic, in chapter 19, I believe section 6, which some of you talked about Tuesday in discussion class, and which we'll talk about in greater detail as we get there, you can calculate K for any reaction if you don't have K given to you by looking at the reaction in question, like this, and examining it to see of what fundamental reactions is this reaction composed. Because the fundamental reactions to which I refer will have K values with which you are familiar. What K values so far have you become familiar with? Ka, Kb, Kw. And in chapter 19 we'll add to that Ksp. And then later on in chapter 19 we'll add to that K sub F, where the F stands for formation. Formation specifically of complex ions. But let's worry about that when we get there. So for now, recognize any K for a reaction for which the value is not given, but a value you need, like this one, will be determinable from a combination in some fashion of Ka and or Kb and or Kw. For component species of the reaction in question, like this. Because if I take this, the equilibrium constant for this reaction, and I multiply this term by hydronium ion molarity top and bottom, which is the same as multiplication by 1. Did we do something like this in chapter 18 early on? Isn't this how we got Kw equals Ka times Kb for a Bronsted-Lowry conjugate acid-base pair? It's exactly what we did, the same thing. I recognize that for this expression that I now have, ammonia molarity times hydronium ion molarity divided by ammonium ion molarity is Ka ammonium ion. And up top, HCN molarity divided by Cn minus molarity times hydronium ion molarity in the denominator is 1 over Ka for HCN. And this information is in our acid-base table. So we put the information in, and there is the K value, 0.90. Which gives us a measurable handle on extent. Now, if we work through this to calculate the equilibrium molarities of each of these species in the system, given that this equilibrium lives in that solution, we would find out how much ammonium ion and how much cyanide ion converted to ammonia and HCN respectively. And then we could write the charge sum for this CB expression. We'll do that in a moment. I'll ask though another question before we proceed. What considerations would we have to make to calculate the hydronium ion molarity for our ammonium cyanide solution? Is this a difficult calculation? It's not. Now, you don't know why yet, at least I don't think you do. unless you're really on top of this material. But whether or not you're really on top of the material right now matters not. Because after what we say, in short order fashion, you all ought to be really on top of the material. That's what we want. Because the next topic is, how do we get the hydronium ion concentration for solutions in which the principal bronze telluric acid-base equilibrium reaction does not involve hydronium ion or hydroxide ion? Does that look like this system? You bet it does. So we'll return to that issue in just a moment. We've already talked about question 1858. Recognize why it's easy to write the charge sum for this. And another feature of writing the charge sum for the iron nitrate solution is to realize that for the principal equilibria for the iron nitrate solution, we've already looked at these. Fe3 quote unquote plus water makes hydronium ion plus quote unquote Fe2, 2 plus. Followed by quote unquote Fe2 plus water makes hydronium ion plus quote unquote Fe plus. Remember those two equilibria? The ions in the system convert to other ions by these reactions. So that would not bring about a problem in trying to set charge balance equal to charge sum, because the species produced by these principal equilibria would be contained in the charge balance expression. That relates to why this is more difficult, because here, for the ammonium cyanide system, the principal species produced by the reaction between ions does not produce ions. So we'd lose sight of these species from a charge balance consideration, wouldn't we? Because you don't find molecules in charge balance equations. Let's take a look at question 1859. Can we or can we not directly write charge sum for this sulfuric acid solution? Well, let's start with the charge balance. Right now, you write charge balance for this system. Write it on your paper. Good practice. At this point, it should not be difficult. You should be able to write it right off. Only cation in the pot is this. The molarity of hydronium ion is equal to twice the molarity sulfate ion plus the molarity hydrogen sulfate ion, and what else?
Hydroxide.
Can we immediately write down a charge sum value, which right now is represented by question mark? What do we know about the charge sum for this system? Is it at least 0.10? Is it bigger than 0.10? Why is it bigger than 0.10? Because at an initial molarity of 0.10, can we well expect that hydrogen sulfate ion will ionize to a measurable extent? And that contributes to the net hydronium ion molarity for the system. So we expect the hydronium ion molarity for the system to compare how to 0.10?
To be
Greater than. But do we expect the hydronium ion molarity for this system to be as great as 0.20? Yes or no? Why not? Because the hydrogen sulfate ion is expected to ionize 100%? No. Not in this system. So all we know so far for this solution, this system, is that question mark equals charge sum greater than this, but less than this. And what would we have to do to get the charge sum? We'd have to calculate the hydronium ion molarity for the system. And what would we do to calculate the hydronium ion molarity for this system? Pay attention to what?
The ionization percent of hydrogen sulfate.
That's right. We look at Ka for hydrogen sulfate ion, get a handle on its ionization extent, which of course gives us the hydronium ion molarity. Now then, let's look at question 1860. Same solute, but we've changed the molarity. We made it 1.0. Well, let's take it as it is in the notes. Just call it 1 times 10 to the minus 5. For this system, we have exactly the same charge balance expression. But for this system, do you think we can write the charge sum value? What is it?
2.20. 0.20.
What is the charge sum value for this system? What is it? The charge sum value. 2 times 10 to the minus 5. Because for this system, at this very dilute m sub I value, to what extent may we reasonably expect hydrogen sulfate ion to ionize? 100%. You betcha. Did we ask you a question like this on exam 1? We sure as hell did, didn't we? You remember the sulfuric acid solution where I told you for the solution the hydroxide ion molarity was 5 times 10 to the minus 8? Remember that? Well, if the hydroxide ion molarity is 5 times 10 to the minus 8, then with Kw you can get the hydronium ion molarity. Can you not? 2 times 10 to the minus 7. Right? 2 times 10 to the minus 7, pretty dilute solution, don't you think? So that was clearly a case where the sulfuric acid solute was ionized completely. Or put another way, the hydrogen sulfate ion was ionized completely in the ionization step involving hydrogen sulfate ion. Now, some of you may be saying, how do I know that hydrogen sulfate ion is ionizing 100% at this molarity of 1 times 10 to the minus 5? Are you asking that question? Do the arithmetic to show yourself that that statement is true. Do the arithmetic. You can do it. Let's try a gee whiz. There's Ka hydrogen sulfate ion. There's the chemical version of Ka for hydrogen sulfate ion. When you folks do these analyses, I suggest strongly you always look at this part first instead of X's. Because once you lose sight of what the hell this X business is, you are in trouble. Now then, let's imagine that the hydrogen sulfate ion goes 99%. Okay? If the hydrogen sulfate ion were to go 99%, rather than 100%. What's the sulfate ion molarity for that solution? And we'll add a significant figure if that's perplexing you. What's 99% of this? Will you take that? What's this going to be? How about that? You happy with that? What's this going to be? Happy with that? Do the arithmetic. And in doing the arithmetic, you're going to get a number that's smaller than this. What does that tell you? The ionization extent is bigger than 99%. The only thing that's left is 100%. You've got to do this arithmetic to let this stuff talk to you. And then the arithmetic part of the puzzle will become easy, because you will have become familiar with it. That's the part you got to do. Now then, we proceed. This. And first consider this. We have talked about solutions of sodium hydrogen carbonate earlier on in chapter 18. We recognize that this solution is, from a pH standpoint, showing what behavior? Acidic, basic, mildly, strongly. Basic and mildly. Because Kb hydrogen carbonate ion is bigger than Ka hydrogen carbonate ion. But each of these K values are pretty small numbers. So you know ionization extent, very small. Okay? What's the principal Bronsted-Lowry acid-base equilibrium in this reaction system? Write it on your paper. Did you write this? Is it not the case that the principal Bronsted-Lowry acid-base reaction equilibrium in this system, as in any system, will certainly involve reaction between the strongest acid, which is a principal species in the system, with the strongest base, that's a principal species in the system? And that stuff is hydrogen carbonate ion. What's the problem? Does this equilibrium reaction produce hydronium ion or hydroxide ion? Can we use this reaction as it stands to calculate pH for the system? Hell no! So where are we going to go? We're going to throw up our hands and say, I can't do it? Like hell. Never. Keep in mind, the only people that ever really fail in life are those who quit. Those who walk away from challenge. Those are the losers. If you try and don't succeed, you haven't failed. You haven't failed. You've gotten benefit from that experience. Maybe from a grade standpoint you failed, as the university will label you. But the only people who really fail are those who quit. Oh well, enough for today's sermon. Where are we going to go to get this pH? System property.
Reactive hydrogen carbon ion with water.
Goody. We'll go to an equilibrium involving a principal species, Bronsted-Lowry acid or base, and write an equilibrium reaction involving another principal species, water, because that reaction will always make hydronium ion or hydroxide ion. Which of these reactions is of greater consequence? We already asked this question. Now we've asked it again. This one, because the K value is bigger. All right? Now then, next question. If we pay attention to this KB reaction, because the K value is bigger, so in order to pay attention to this KB, we wrote out KB. In what way can this equilibrium constant expression be used to give us a handle on the hydroxide ion concentration for this system? Can we use this equilibrium reaction as it stands to calculate correctly the hydroxide ion concentration?
No.
Why not?
Multiple sources of carbonic acid.
Could we to this system legitimately apply x squared over m sub I minus x? No, why not? What you said related to this. Next question. In regard to the x squared over m sub I minus x not being applicable to this equation. For this system, how does the molarity of this compare to the molarity of this? Because if x squared over m sub I minus x does not apply, it means that the quote-unquote H2CO3 molarity and hydroxide ion molarities are not the same. Well, then one's larger than the other. Which one's larger? The answer's on the board. Which one is larger? The quote-unquote H2CO3 molarity is larger. Why? The answer's on the board.
Because of the first reaction.
You see that first reaction? Is the extent of that first reaction larger than the extent of either of these? Is the K value for the first reaction larger than either of these Ka or Kb values? How do we know that? Is it the case that hydrogen carbonate ion is not only a stronger acid, it's also a stronger base than water? Right? So the K value for that top reaction has got to be bigger than 2.4 times 10 to minus 8. Of course it's bigger than 4.8 times 10 to minus 11. Some of you look mesmerized by this. Which means I have in this system two sources of quote-unquote H2CO3. I have this reaction and I have that reaction. But how many sources of hydroxide ion do I have? Just one. Means guarantees the molarity of this is bigger than the molarity of that. Now let's finish today's conversation by getting the K value for this reaction. The principal AB equilibrium reaction. Let's give it a designation of circle star. K circle star is this. How do we calculate it? Because we want the K value. Will this allow me to calculate it? The same trick of sorts I use to get K for our ammonium cyanide system. Can I apply this? Will this work? Well, what will I have in the denominator? I mean, what do I have as far as K's are concerned? I got bicarb in the denominator, molarity, carbonate times hydronium ion molarity in the numerator. What's that correspond to? What is it? Bicarb molarity denominator. Hydronium ion, carbonate ion molarity numerator. Does that look like Ka up there? What's left? Hydrated CO2 numerator, bicarb molarity denominator, hydronium ion molarity denominator. What's that? What is it? What is it?
1 over Ka.
1 over Ka for that stuff. That stuff being hydrated CO2. Put in the numbers, see what you get, and see if from this point you can proceed to calculate the hydronium ion molarity for this system. We'll pick it up from this point on Monday.